So your TA Serenity is totally amped up right now. She loves windows. Right, windows are basically like kitty TV. So we're going to solve two versions of this double-paned window problem. One with stagnant air on the inside, and one where the space in between the windows is a vacuum. And you're going to learn how to set up one-dimensional conduction problems as equivalent electrical circuits using thermal resistances. So start off writing down all of my constants from the problem statement. The two things that I'm going to try to find, Q dot for air and then Q dot for vacuum. And I'm going to be solving this as a thermal resistance problem where I'm going to model the one-dimensional conduction as an electrical circuit, with each stage of conduction, convection, or radiation as essentially an electrical resistance, a thermal resistance. But now for each Q dot, I'm going to make a different set of assumptions. So with stagnant air in the middle, I'm going to first assume that I can ignore radiation. So for most of your heat transfer course, you will be ignoring radiation for almost every problem, because for most problems, radiation is actually going to be negligible. Most heat transfer for most engineering purposes is conduction and convection. We are going to see later on in this problem that the radiation is actually not negligible, but I am going to make that assumption this time to show you because that's what you normally do and to show kind of a contrast how you could recognize at the end when it's not negligible. Second assumption is I'm going to ignore convection through the stagnant air. That's that keyword. Stagnant means that the air is not moving. And you can't have convection if the air is not moving, right? That's what convection is. It's actually heat transfer through a moving fluid. So if the air's not moving, then there's only conduction through the air. And some good assumptions to make for every problem is that we're going to assume that heat transfer is one-dimensional. We're only looking at basically the horizontal direction. And that essentially means we're ignoring everything that happens at the very top and the very bottom of the window. We're only looking at what is happening horizontally through the middle. Looks like your TA has some important kitty business in the other room, so we'll check on her later. The last assumption you probably want to make for most problems this semester is that material properties are constant. In reality, the thermal conductivity of glass is different at different temperatures. Like it probably gets smaller at warmer temperatures and it's larger at lower temperatures. But since most of the temperatures in this problem are really close together, we can probably ignore those differences. So just assume that material properties are constant. So I start off by drawing the electrical circuit with thermal resistances for heat transfer through this window. So I'm going to include 5 different resistors. So starting from the 21-degree air on the inside of the window, we first have convection, natural convection from the air to the surface of the window, which I've labeled as T1. Then we've got conduction through the glass to T2, which is the temperature at the inside of the glass. Since there's no movement of air on the inside, there's no convection, and for this first part, I'm ignoring radiation. This means that there's just going to be conduction through the air in between the two panels. So from T3, which is the temperature on the inner surface of the outer pane of window, to T4, which is the outer surface of the outer pane, we've got conduction through that second pane of glass. And then outside from T4, the outer surface of glass, to the -5 degrees outdoor temperature, we've got convection from the solid surface out to the air. All right, so then electrical circuit for the second part where we've just got a vacuum in the center. It's going to be almost the same thing. You've still got convection from the air inside to the surface of the glass, conduction through the glass. If there's no air in between, there can't be conduction through the air or there can't be convection from moving air. The only way from heat to get from one surface to the other through a vacuum is radiation. So we'll put a resistance there for radiation jumping from the inside of one pane to the inside of the other pane. Then we still have the regular conduction through the second pane of glass and then convection out to the cold air outside. So the two circuits are almost the same as each other. We just swap out the convection term for a radiation term. And of course, keeping in mind that in the air problem, I ignored thermal resistance due to radiation. If we had included radiation in the problem, there would actually be 2 resistors in parallel in that middle section. Basically, heat can go from one pane to the other, either through convection or through radiation, right? 2 different paths, 2 different parallel resistors in that middle section. So now I'm writing down the 3 different regular equations that you will use for convection, conduction, and radiation thermal resistances through a plane wall, essentially. The L over Ka for conduction is going to be really common. You'll use that all the time. 1 over HA, also super common term for convection. You'll use that a million times. But this radiation resistance is pretty strange looking, and you can tell by how big the term is that it's kind of weird, and you're probably not going to be using it very often. So it's actually worth taking a super quick diversion here for a minute to show you where these resistances actually come from, because you could conceivably given problems where you have to invent your own thermal resistance, where you can't just look up R in your textbook and you have to actually kind of create it yourself. So the main normal equation for one-dimensional conduction through a wall is Ka delta T divided by the length of the wall. And for an electrical circuit, Ohm's law, V equals I times R, we rearrange that as I equals V divided by R. I is current, that's the thing that flows, so that's Q. V is voltage, that is potential. Electrical current goes from high voltage to low voltage. And in heat transfer, heat goes from high temperature to low temperature, so temperature is your potential, that's your numerator. And electrical resistance is the denominator R, so in heat transfer, that's basically everything else. All of your K, area, length, H, like everything else in your heat transfer equation, that is your thermal resistance. So if 1 over R is everything else in your equation, then we can see that for conduction through a plane wall, R is equal to L divided by Ka. That's where this term comes from. So you don't necessarily actually have to look up thermal resistances. If you have your equation for Q, you can actually just grab thermal resistance as everything else. So your regular convection equation, HA delta T, right? We've got really easily Q and delta T are already kind of there. So 1 over R is the HA, it's the everything else in your equation. And rearrange that, you get that the R for convection, thermal resistance for convection, is just going to be 1 over HA. It's all the other stuff in your heat transfer equation for convection. Now, radiation, though, is going to require a little bit of algebra, because looking at this regular radiation equation, you see, we don't just have delta T. We've got both of the temperatures are raised up to the 4th power. So this is going to take some algebra to try to rearrange these temperature terms to get just a regular delta T with no exponents. So since there's a subtraction sign in between these two temperature terms, we can split this T to the 4th minus T to the 4th into two separate T squared terms, once with addition and once with subtraction. And you can see if you multiply the two first terms, you get a positive temperature to the 4th. If you multiply the two second terms, you get a negative temperature to the 4th because one of them is subtracted. And from FOIL, if you do like the insides and the outsides, those terms are going to cancel because one of them will be added and one of them will be subtracted. All right, halfway there. Now we just take the second half of this, the one where now we have a temperature squared minus temperature squared, and split that into two separate terms, one with an addition and one with a subtraction. And so now you can isolate the delta T is just this last set of parentheses, and your 1 over R is everything else. All the stuff we started with, plus all of these new parenthesis terms, the temperature squared and the temperatures by themselves. So this is why the radiation thermal resistance term is so much more complicated looking than the convection and conduction equations. It's because radiation is based on temperature to the 4th, and it takes all this extra algebra to isolate delta T by itself. All right, so time to plug in some numbers and let's actually make some progress towards getting to an answer now. So this is for the first electrical circuit where we're assuming there's air in the middle. We've got 21 degrees and -5 degrees up in the numerator. And then the denominator is the 5 thermal resistances all added together because they're all in series. We've got a 1 over HA at the beginning and the end. That's the convection on the outer surfaces of both windows. Then moving inwards, we've got two conduction terms, L over Ka for both of the glass panes. And then the very center is going to be another conduction term, and that's L over Ka for the air that's in the middle. We're given the convection coefficient on the outside surface, which is going to be 10 watts per meter squared Kelvin. And the size of the window, we can multiply the dimensions and get 3.6 meters squared. So this is a pretty big window. So through the glass, we've got 3 millimeters thick. All right, and the problem statement gave us K value for the glass, which is good. That saves us the trouble of having to look it up in a table, which a lot of times you will have to actually look up these K values in a table in the back of your textbook. But for now, just plug in the 0.78 that we were given. Same surface area, right? This 3.6 meters squared is going to be the surface area for all 5 of the resistors. Move on to the air in the middle, 1.2 centimeters for this gap. Given 0.026 for the conduction coefficient. So air is kind of an insulator. Air does not conduct heat very well. Things like metal are going to have very high values for K. Insulators will have very low values for K. Second pane of glass, exactly the same as the first one, the 3 millimeters in the numerator and the 0.78 in the denominator. And then for the convection on the outside of the window, we had a larger convection coefficient on the outside, 25 degrees. And that might happen because there might be a little bit more wind, say, outside this window. If the air is mostly still on the inside, H will be a little bit lower. If there's a little bit of wind on the outside, that forced convection will make a little bit larger value for H outside the window. All right, some calculator work with all these fractions in the denominator. I get a combined thermal resistance of 0.1692 after I add up all the terms in the denominator. And that gives me 153.7 watts for Q dot for this problem where we just have conduction through air through the center. And we'll do the same thing one more time for radiation, where all of the convection and conduction are going to be the same, except for the very center conduction term through air. I'm going to replace that with the radiation term. So first I'll go ahead and write down all of my resistances for conduction and convection, because again, those numbers haven't changed at all. Same L, K, A, and H as before. All right, so now for the radiation resistance, this first value epsilon is the emissivity of the material. For simplicity, you could just assume a value of 1, but I'll go ahead and look this up in a table and I'll see 0.94 as the emissivity for glass. This next value sigma is just a constant. It's the exact same number no matter what your material is. So you just look this up, the Steph Curry constant, the Stephen Boltzmann constant. Yeah, so the Stephen Boltzmann constant. So the Stephen Boltzmann constant is named for scientists, not basketball players. And it's so 5.67 times 10 to the negative 8. And you see that this number, 10 to the negative 8, is a super tiny number, but it has to be really small because you've got temperatures raised to the 4th power. And those are going to be temperatures in Kelvin. So that temperature term is going to be enormous. So the Stephen Boltzmann constant, 5.67 times 10 to the negative 8. And then area A is just the same 3.6 we've been using for all the surface areas. Now here's the problem though with temperature. The relevant temperatures here are not the 21 degrees and negative 5 degrees that are the air temperatures. The relevant temperature in this radiation equation, the radiation is going from the inner surface of glass to inner surface of glass. We need to know the temperatures of the glass at that point, which we don't know. And this is going to lead to the solution method that students always hate, which is going to be an iterative solution. You just have to guess temperatures, solve the problem, and then check and see how good your guesses were, and then solve it again with better guesses. I know you hate this. I hate it too. There's just no better way. So without any good reason to choose, I'm just going to assume that there's a change in temperature of 10 degrees through each section of glass. So I'll choose 11 degrees on the inside of the inner pane and 5 degrees on the inside of the outer pane. Again, it doesn't really matter what you guess. Just guess. Just make your best guess and move on. So I convert these temperatures to Kelvin, 284 and 278, and get a thermal resistance for radiation after some calculator work, 0.058. And plug that into the numerator of my big term as the center resistance of my 5 resistors in series. And I get a combined thermal resistance now of about 0.099. And that gives me a value of Q dot of 260.9 watts. But this is not my final answer, because remember, I just randomly guessed 2 temperatures. So what I'm going to do now is I'm going to use this heat transfer rate to solve for what the temperatures would be at the inner surface of the glass and use those temperatures to come up with a new, better answer. So I start off with a really small thermal circuit at the inside from the 21 degrees through convection, through conduction through the glass to this inner surface of the inner pane of glass. So it's the same convection and conduction terms I already calculated. And so this time, instead of solving for R or Q, I'm using my known Q, my known values for R, to solve for this temperature at the inner surface of the inner pane of glass. And I get 13.47. So instead of a 10-degree drop, it was only actually like an 8-degree drop. So now we'll do the same thing from the outside. From the -5 degrees, we go through the same convection resistance and same conduction resistance through the glass to find out the temperature at the inside surface of the outer pane of glass. And from there, we get -1.82. So it's actually even a really small change, only like a 3-degree change out there. There's a much smaller drop on the outside because the H value was larger, right? Heat transfers a lot easier on the outer pane, so heat goes through easier, which means a smaller change in temperature. So we convert these two temperatures into Kelvin, about 286 and about 271, and we plug these temperatures back into my radiation resistance term to get a new radiation resistance. So instead of 0.0586, I'm 0.0599. So using this new value for radiation resistance in the denominator, I get 0.101 as my overall thermal resistance in my denominator, and get a new value of Q of 257 watts. And if I really wanted to, I could use this new value for Q and use that to solve for another new value for each of the temperatures and keep iterating. But since this update only resulted in a 1% change in Q, I think we're basically good enough. This is close enough to the final answer that we can stop here. And so now let's compare the two values of Q that we got. We got Q using conduction of air as 153 watts, and Q using radiation of 257 watts. So what this tells us is for this problem, ignoring radiation was actually a mistake on the first half of the problem. Right? Radiation for this case is not negligible. Radiation is going to be negligible when you have really large values of K or H, which are going to result in a lot of heat transfer through convection and conduction. So when you have really small values of K or H, which means a lot of resistance to heat transfer, those are the times when you actually should include radiation. So the easy part of this problem is that all of our heat transfer was horizontally and our electrical circuit was entirely in series. If you want to look at a more advanced thermal resistance problem where some of your resistances will be in parallel with each other, that's the video linked up on the screen now, and that'll be the perfect one to watch next.